Hi, good morning everybody. Let's take a look at question 1 of the H1 Chem FA. For the first question, I think I don't need to go through with all of you how to do. Okay, you just need to assign X for the oxidation state of sulfur, okay, and then you work out accordingly. So just to give you an example, okay, for the benefit of those who really don't know, okay, so for the part D, okay, since you have 4 sulfur, so 4x plus 6 oxygen, each oxygen has -2 and overall is equals to -2. So that's why X is equals to plus 2.5. Over here, just like to highlight, okay, all your plus must be in front of the number. So if you give something like 2.5 plus, you will get it wrong. Or if you write 2.5, similarly also wrong. Okay, so this is just a convention. Please take note. For question 2, let's take a look. A nail of mass 1.4 gram, okay, it was dissolved in an excess of dilute sulfuric acid to form 100 cm³ of solution. So I have over here 100 cm³ of my solution. And in this case, they say out of this solution, I took out 10 cm³, okay, for titration. So over here, I have 10 cm³, and in my burette, I should have KMNO4 for complete reaction. And they specifically mention that it is assumed that all the iron in the nail, okay, which means the Fe in the nail, was converted to Fe2 plus when dissolved in dilute sulfuric acid. So this equation shows you the conversion Fe to become FeSO4, whereby Fe2 plus is the component, okay, of FeSO4 in aqueous solution. So which means to say, in this solution, actually I have 100 cm³ of Fe2 plus because the iron already dissolved to give Fe2 plus. Similarly, I took out 10 cm³. This 10 cm³ also contains Fe2 plus. So based on this, you are able to see very clearly that it is our Fe2 plus that reacts with KMNO4. That's why in this case, okay, for our oxidation half equation, it is Fe2 plus to become Fe3 plus, okay? Some of you actually put Fe to Fe2 plus, okay? Which is wrong, because I think you are confused by this equation, but this equation only wants to tell you that when the iron dissolves in acid, it will form Fe2 plus, and it is this Fe2 plus that subsequently reacts with KMNO4. So be careful when you read the question. Then for KMNO4, well, we know KMNO4 can only be reduced, so it must be under the reduction half equation, and we know that it is an acidic medium, so we must reduce it to Mn2 plus, okay, not MnO2. Please take note. So based on this, we can get an overall equation. Because the oxidation half equation has 1 electron, the reduction half equation has 5 electrons, so you times 5 for the oxidation half equation, and you add up left hand side and left hand side, right hand side with right hand side, you should be able to get the overall equation. You should be able to get the overall equation. Okay, so next thing, part B says, assuming the mole ratio between MnO4 minus and Fe2 plus is 1:5, can you calculate the percentage of iron in the nail? So let's take a look. The question gave us that the manganate needed was 4.0 times 10 to the power of -4 moles. So in this case, you look at the equation that you have constructed. Over here, it is 1 mole of KMNO4 is to 5 moles of Fe2 plus. So if you have used 4.0 times 10 to the power of -4 moles for Fe2 plus, you just need to times 5. So you will get 0.002. Not forgetting, this is only in 10 cm³ of the sample. If you want in 100 cm³, which is the original sample, you need to times 10, which is 100 over 10. Okay, you get 0.02, and you need to find the mass. So the mass is simply just multiplied by the AR, which is 55.8. You will get 1.116 grams. And they want percentage of iron. So the entire iron weighs 1.4 gram. So this 1.116 divided by 1.4 times 100%, you should be able to get 79.7%, which is the percentage of iron in the nail. Okay. So one common mistake here is a lot of people left out the second step. Okay. This is very, very important. We always do standard, we always make a standard solution, then after that take out a certain portion to do titration. So take note, okay, that this procedure over here, when you work backwards, you remember to times the dilution factor, in this case, which is 10. Okay, please take note. Moving on to question 3. Okay, question 3a, I think nobody has any problem. State the oxidation number. All of you managed to get +7. All of you also managed to get the oxidation half equation for Ti3+, because the question already mentioned to you that it is oxidized to Ti4+. So nobody has any issues with the oxidation half equation, which is good. Then part C asks you to determine the number of moles of electrons received by 1 mole of ClO4-. Let's do this step by step. Okay, do it systematically. I will show you 2 methods. Okay, show you the first method first. Okay, so they actually mention that 1.25 times 10 to the power of -3 moles of ClO4 reacted exactly with 0.01 mole of Ti3+. So in this case, based on your equation, half equation, I have 1 mole of Ti3+ actually donated 1 mole of electrons. So if I have 0.01 mole of Ti3+, I would donate 0.01 mole of electrons. Okay, this is specified by this statement, which you do have to write down this. Next, we know that for all redox, okay, just a recap, moles of electrons gained is equals to moles of electrons lost. So in this case, Ti3+ actually lost this amount of electrons, or you say donate this amount of electrons. So ClO4- must be the receiving party. So they tell us that I have 1.25 times 10 to the power of -3 moles, which is given in the question. Okay, this is given in the question. Okay, and it received this number of moles of electrons. So the question wants you to find out how much is gained by 1 mole of electrons. So this part is solely by proportion. Okay, this part is solely by proportion. Okay, so 1 mole will receive 0.01. Okay, divide by 1.25 times 10 to the power of -3, of course, times 1. Okay, equals to 8 moles. Okay, so this is my first method. The second method is actually using the table method, which I will show you. Okay, so the second method is simply you draw this table that all of you are very familiar with. So over here we have ClO4-, and in between will be the electrons, and finally Ti3+. Alright, the ClO4- reacts with the Ti3+. And then of course our first row is our moles of compounds. Then after that we have our mole ratio. Then after that we have our moles of compounds to electrons, and finally we have our common ratio. So this few headings, you have to remember it very well so that you can sub in the values easily. Alright, let's take a look. So ClO4-, I actually have 1.25 times 10 to the power of -3. This is given in the question. Ti3+ has 0.01 moles, also given in the question. And the mole ratio is simply just 1:8. And In this case, we actually know that Ti3 plus is being oxidized to Ti4 plus 1 electron. So our moles of compounds to electron is simply just referring to this. Alright, so we have 1 is to 1. So for common ratio, very simply, okay, so look column by column. So we have column by column. So this one must be 8. So from 1 to 8 we times 8. So from 1 to 8 we times 8. We should get 8 over here. And we know that from 8 to 8 we times 1. So from over here also times 1. So it is actually 1 is to 8 is to 8. Okay, or you can write out. Okay, it is actually 1 is to 8 is to 8. So straight away from this, you will be able to see that 1 mole of ClO4 minus actually receives 8 mole of electrons. Okay, so there are two methods to doing these questions. Either one will do. Alright, so let's take a look at part D now. Hence, determine the oxidation number of chlorine in the product. Okay, so in this case, right, requires you to think a bit. Initially, you have ClO4 minus and the oxidation number is +7. So I know that in this case, I receive 8 moles of electrons. Okay, so what I can do is I can actually rewrite this portion, okay, as a reduction half equation. So let's say Cl, let's say 7 plus, and I actually receive 8 electrons. So very simply, 7 plus 8 electrons, you should get minus. So Cl minus, alright? How you get it is plus 7 minus 8. Because electrons is negative, you should get -1. So in this case, your product should be a Cl minus. Please take note again that your negative sign should be in front of 1. So let's say if you write 1 minus, your answer will be wrong. Okay, again, this is just a convention for you to put your sign in front of your number. Let's look at the last question, 4a. Actually, for 4a, I think this is a very simple question. Okay, we always, let's say if you have more than 18 electrons, always fill in 4s first. If you want to remove electrons, you also remove from 4s first. Okay, so this one I will leave it on your own to do it. I'm sure you can do it. So this question actually asks you to sketch the shapes of all the orbitals that can be found in an oxygen atom. So as a thinking process, oxygen atom, we actually, you notice in the previous part of the question, we filled up all the way until 2p. That's why in this case, the orbitals found in an oxygen atom will be 1s, 2s, and 2p. So the question is very nice. They have already given us the sketch of the diagram. So you notice that they actually gave us the axis. So take note, next time if you are required to draw the orbitals, you need to show the axis, because we know that all these orbitals are actually present in a 3-dimensional space. Okay, so even though you are just drawing a round circle, okay, you need to draw it in terms of a sphere. Okay, you need to show the 3D shape. Then in this case, you have 2p to show as well, but the question actually just asks you to sketch a 2px orbital. So you need to have the axis x, y, z and show that for the 2px, it is aligned to the x-axis. For part C, I think all of you should be able to do it on your own, so I will not go through this part. Okay, you just need to be very sure of your equation. Should be deflection angle proportional to charge over mass. And over here, your mass, please take note, it refers to the, okay, let's say I have an ion, let's say Y, X plus, okay, and A and B. It refers to the number on top. Please take note. Some of you actually use the mass number as the one below, which is wrong. So please take note, it's the mass number on top. Okay, so we have come to the end of the H1 Chem FA2 corrections.